going to look at functions. We're going to kind of introduce the main functions that are out there, and then later on in this chapter we're going to learn how we can transform these functions, stretch them, compress them, move them about. But first we need to have a pretty good idea of the main functions and kind of their key elements. So we're going to start off with probably an old friend for you, linear functions. Well, as the name implies, the graph of a linear function is a line. And so we have this form, which you might remember, slope-intercept form, the most practical form for a linear equation, where this little number here represents the slope of the line, and this number over here represents the y-intercept. So an example might be something like y equals 2x minus 1. And just to refresh your memory how easy it would be to graph something like this, we have a y-intercept of negative 1, so we have to go down 1. So we know our line is going through this point, and we have a slope of 2, and I will think of that slope as 2 over 1, so that I can think of a rise over a run. So from this point, I have to build a slope triangle that has a run of 1 and a rise of 2. So we'll just go 1 to the right and up 2. So there's my little slope triangle. Okay, and there's my line. Whoops. Well, you get the idea. A ruler does help for those who want to do a really straight line. Okay, so that's all I'm going to say about a linear function. The next function that I'm going to look at is perhaps not familiar to you. It's called the absolute value function. And it looks, first look, absolute value. And it basically looks in its equation like this. We have these absolute value lines, and those tell you that the number that is in between has to be turned positive. And its graph gives you a kind of a distinctive V shape. And that's our sort of typical absolute value graph coming down to a point. And these are actually 90 degrees to each other, although as we'll see in this chapter, that's quite changeable. Next one is perhaps also an old friend, quadratic functions. The quadratic function is any kind of function that involves an x squared. You can't go higher in exponential value than that, but you can have an x term and perhaps even a constant tacked on. This is the basic, most simple form of a quadratic. And if you think back to a table of values or something, you would have 0, 0, 1 to the right, and up 1, 2 to the right, and up 4 as a couple of points. So that would be the right side of our graph. And of course it is symmetrical. So what we have here is a parabola. And down the middle here is our axis of symmetry. The equation of this axis of symmetry is x equals 0. And this point here is 0, 0, is our vertex, kind of the minimum point in this particular parabola. Okay, and again, I'm not going to say much more about that. Perhaps you've also seen with parabolas, just to refresh your memories from the good old days, you might have remembered this form here where we had this kind of possible transformations occurring. And maybe I'll do one example just to make sure that that's all correct. We don't want anybody going through the chapter with something maybe that you remembered wrong. So maybe I'll do a quick example here of, let's say, negative 2, and we'll go x plus 3 squared minus 1. So how would I graph that? Well, First thing I would do is get all the shifting done. I can see the whole graph is pulled down 1, so I'm going to go down 1 and mark that with a dotted line. The other shift on the x-axis is to -3, so that's 3 to the left, and I mark that with a dotted line. So what I've done is I've taken my shifting and I've said, okay, my shifting is taking my vertex to that location. Now that I'm at this location, I want to see what the graph itself looks like, and I kind of mentally anyway run through a very simple table of values. What I'm doing is saying to myself, how does the remaining function, that is y equals -2x squared, the function without the shifting, how does that behave? If I went, say, 1 to the right, maybe 2 to the right, what do I get? Well, 1 to the right would give me 1 squared times -2, so I'm going to get -2. 2 to the right would be 2 squared, 4, times -2, so, oh my goodness, -8. So I go 1 to the right, then I'm supposed to go down 2, and if I go 2 to the right, I'm supposed to go down 8. Well, that you can see is way down here. I'm just going to say way down here somewhere. What I'm getting is a very narrow graph that opens down. Whoops. It's supposed to be symmetrical here. My axis of symmetry is x equals -3 in this example. My vertex is -3, -1. So that's just to refresh your memory about quadratic parabola graphs. Okay, let's look at the next one up. We looked at the squared. What about something cubed? Well, I'm going to look at a very, very simple one here. Of course, these are called cubic functions. And we want to look at the most basic, y equals x cubed. Now, I could go ahead and produce a table of values, much like I did for the parabola. But I'm just going to go ahead and sketch that out. And if you're interested in the table of values, you can kind of figure those out as we go. I'm just going to mark them straight on the graph. For example, 0 cubed is 0. 1 to the right, 1 cubed is 1. -1 cubed is -1. But here's where it starts to grow quite rapidly. 2, I plugged in 2 and cubed it, that would go up 8. So I'm way up here now. So really we're getting this kind of a graph. And then it does the same sort of thing going down in the negative direction. So that's the basic shape of a cubic graph. The next one I'm going to look at is called a rational type function. And very basic form that we're looking at is 1 over x. You might be familiar with that. It's kind of an interesting graph, and it comes in 2 sections. The reason it's split into 2 sections is when x is 0. When x is 0, this thing is undefined, and so there's a split. What we'll come to learn is actually a vertical asymptote. So what's happening is this. You're going to get a few points over here to help guide you. Like if you put in a 1, you'll get a 1. If you put in a 2, you'll get 1/2. Very similarly, if you put in some fractions like 1/2, 1 divided by 1/2 would be 2. So you're getting that kind of thing. So you're getting this kind of a shape in this positive quadrant, and we're going to get the same thing happening down here, this negative quadrant. For example, if you put in -1, well, you get a resulting y value of -1. -2 goes to -1/2, and -1/2 actually goes down to -2. So we're going to get the same basic shape that we have in this quadrant occurring over in this quadrant. The interesting things about this graph is that we have a vertical asymptote at x equals 0, but we also have a horizontal asymptote at y equals 0. So not only has it got 2 components or 2 sections, we have a vertical and a horizontal asymptote. Okay, the next function that's up to be analyzed here is the radical. And as the name implies, these are functions that involve a radical. And the most simple one that we're going to look at is the square root of x. This is an interesting graph because it only starts to exist when x is 0 or greater. It's simply, there is no graph on this side. You can't put a negative number in and take the square root of a negative number. So it only exists in this positive zone. So the shape looks something like this. If you put a 1 in, the square root of 1 is 1. If you put in a 2, it's not easy to spot, but the square root of 2 is a little bigger than 1. The next easy one actually is when you plug in a 4, because the square root of 4 is 2. So our graph looks something like this. Now this is supposed to be a nice smooth curve. I don't know why. I just wanted to wobble on me, but it's actually consistently growing as we move along to the right. So that's the radical function. The last function that I want to talk about is this one, the exponential. A very important function when we get to talking about logarithms. But just to give you a basic idea, there are two sort of main groupings of exponential functions. The ones we're talking about here is when we have a number, which I'll just call a base, to the x. The two main groupings would be this. The base can be a fraction. So I'll do something like 1/2 to the x. And the other thing that the base could be is a number that's bigger than 1. So something like 2 to the x. So this gives you kind of the two main groupings, fractions or numbers greater than 1. Notice these bases are always positive numbers. What would this graph look like? Well, we can start with a really nice point, and that is when x is 0, because this 1/2 to the 0 is 1. Okay. If we put in a 1, 1/2 to the 1 is just 1/2. If we put in -1, 1/2 to the -1 is positive, or yes, it is positive 2. And so what we're going to get is a kind of a funny graph. It goes like this on the left side, and on the right side it steers always closer to the x-axis, but never, of course, reaching it. So we actually have a horizontal asymptote at y equals 0, no vertical asymptote, at a very important point at 0, 1. It's funny because this point is duplicated even when the base is different. We have this point when x is 0, 2 to the 0 is 1. So that point duplicated. This time, however, if we go and put in a 1, 2 to the 1, well, that's 2. And if we put in a -1, 2 to the -1 is 1/2. So you kind of get the same sort of shape, except it's flipped over. It's kind of reversed, spun around, as it were. And so again, we have the same horizontal asymptote is occurring at y equals 0. So that's where I think I'm going to stop for now. These are our basic functions, and it will really help you in this chapter and other chapters if you have a really good command of these functions, able to just draw them without rushing to the calculator. Of course, you can just put these into your graphing calculator and have a look at the picture. But it's really nice if you have a good, solid command of what the basic graph would look like. And that's what I've done here. So, with that, we'll catch you later. Hello, and welcome to today's lesson. Today we're going to look at horizontal and vertical translations and have a look at how that affects graphs of some of the functions that we've looked at in the previous lesson. We're going to start off with the vertical translations because they're a little bit easier to see. So here's the kinds of things that we're looking at. We'll have some kind of a function. Could be exponential, could be an absolute value, could be quadratic, any of those functions. And what we're going to do is make the following transformation. We're going to take that and tack on some kind of a number. And the effect of that number that's tacked on is it will lift the graph or pull the graph down vertically. So let me start with a very simple example. What I'm going to do is take a quadratic function and take our favorite parabola and tack on a 3. What effect does that do on our graph? Well, it's very simple. Essentially, you have to think of the original graph, x squared, the most basic parabola, and think, well, I'm now going to tack on this plus 3. What that will do is shift the graph up 1, 2, 3 vertically. And at this new location, we're essentially going to just redraw the graph of y equals x squared. So that what we're getting is a congruent graph to the original. In other words, y equals x squared and y equals x squared plus 3 are identical in shape. These graphs are congruent in every respect. The only difference is that this one has been translated up 3 units. So if we remember a few key points to help us get the shape of the parabola, such as we have 0, 0, and we know if we go 1 to the right, then we go up 1. If we go 2 to the right, we go up 4. And we know it's going to be symmetrical. So we know that's the right half of our parabola, and here is the left half. So essentially, that's really all there is to these kinds of vertical translations. Let me show you how that might look with a different graph. Okay, let's take something like comparison of y equals the square root of x, which we looked at in the previous lesson. And now what I'm going to do is now tack on a 2. What's that going to do? Well, we're simply going to take the original function, the square root of x, and move it up 2 notches. So I like to draw that in with a little dotted line. For me, it's kind of a little guideline, and then I just say, well, if I now kind of ignore the shift and say I know I've moved it up 2, but what does the square root of x behave like at this location? Well, root x starts at 0, 0, 1 to the right and up 1. And if we want to get fancy, we can do as many points as we would like, but I don't think I want to get fancy. There's my graph. That's all I need to do. I've got a pretty decent graph. So that's vertical translations. But now a little bit more, perhaps a little more confusing at first, is the role of horizontal translations. So first of all, how do we compare those? What's kind of the big picture? Well, for the horizontal ones, what we're going to do is, again, take our function and say, well, what modifications do we do to f of x that produce a horizontal shift to the right or left? Well, what we do is this. You have to tack right into the function, so it's going to be inside the function, something, I'll just use h here, something with the x. Now, it can be that it's going to be added or subtracted. I wrote this as x minus h. But what is important is that it kind of behaves opposite. The way I like to think of this is, and maybe I'll use numbers here. I think that'll make it more clear. Let's use a square root function again. So this time what I'm going to do is say, well, what if I had x minus 2? Sort of tucked right into the square root function. Well, this is going to produce a horizontal translation or shift, but should I go to positive 2 or negative 2? That's always kind of the source of confusion. Here's an easy way to remember it. Just ask yourself, what value of x makes this 0? Okay, and the answer is that, well, the x value that makes this 0 is positive 2. And that's where you want to do your shift. You want to go to positive 2, because positive 2 minus 2 makes 0. And if you remember that, it's an easy way to keep it clear. So let's draw a little picture. This time, I'm going to go to the right to positive 2. Okay? And if I want to, I can even draw a little dotted guideline and say, well, that's kind of like where the y-axis has been shifted. And I'm going to do my 0, 0, 1 to the right, up 1, and there's my square root graph. Okay, again, it's congruent in all respects to this graph here. It's just been shifted 2 to the right, whereas this one's been shifted up 2. Okay. Well, I think we need to look at a couple more examples, and then pretty much that's all there is to the transformation game, at least with vertical and horizontal translations. All right. Okay, let's have a look at something like this. This one I'm going to make a little more complicated. Let's say we had the absolute value function, and we had a couple of translations going on here. Well, what you have to do is ask yourself, okay, horizontally, what's going on? Well, in here, inside the function, I have x plus 1. So that means I'm going to be shifting to negative 1, 1 to the left. Vertically, what's going on? Well, the whole thing's being pulled down 2, so minus 2. So now, let's have a look at our graph. We want to go 1 to the left, okay, and we want to pull the whole thing down 2, so down 2. So this is where the vertex of the graph is going to be. And you have to just remember, when you see an absolute value graph, you're expecting it to be some sort of a V shape. And so this one has no other modifications, so it'll go 1 to the right and up 1, 1 to the left and up 1. So there's our absolute value graph in its new shifted and modified location. Okay. Well, let's just look at one more that's even more complicated. We'll make this our final example. What often happens is we try to look at modifications on graphs of functions that we don't actually know the algebraic description. That is, we have a graph, we have a picture, and we want to show what some modifications would do. For example, I'll just make a kind of a strange looking one here. Okay, in this case, I've decided to do something like this. Go 3 to the left as one important point on my graph, and 0, 0. And I'm going to do a little kind of a semicircular part here. And then I'm going to have a line that kind of goes roaring up like this. And then on this side, I'm going to do the same thing. So this is going to be my f of x. And what we might be asked to do is graph y equals, and we're going to throw in some modifications here. We might go f of x plus 3 plus 4. Now we got to figure out what are we going to do, and here we have our translations, and we don't really know the algebraic structure of the graph. Well, no need to panic. All you got to do is say, well, horizontally, I want to take my points and shift them to negative 3, 3 to the left. And vertically, I'm going to take my points, and I want to shift them all up 4. So as far as the y-axis shifting is concerned, I'm going to move, the y values rather, everything's going to move up 4. So let's see if we can get a decent picture here. Okay. So I want to move everything 3 to the left. So 1, 2, 3. Okay, little dotted guideline. Everything gets shifted up 4. 1, 2, 3, 4. And at my new location, I've got to try to redraw a congruent version of this graph here. So what do I need? Well, I got 0, 0, so that should stay there. Then I've got 3 to the left, so 1, 2, 3. And then I got my semicircle. Okay, so that's all there. Then I go roaring up at basically 45-degree angles, so no problem. And then I do the same thing basically over here with a negative slope. Well, there's my picture. Okay, so that's basically all there is to horizontal and vertical translations. So we'll catch you later.